presentation is on the Berezin range of composition operators. In this talk, I will present the convexity of the Berezin range for some particular classes of composition operator, and I will discuss when the origin belongs to the Berezin range or the closure on the Berezin range. And first, I start with the definition of reproducing kernel Hilbert space. For any non-empty set omega, if omega c denote the set of all function from omega to c with the additional structure pointwise addition and scalar multiplication, and with this structure, this f omega c, this becomes a vector space, and a subset h of f omega c is said to be a reproducing kernel Hilbert space on the set omega if h has the following three properties. First property is H is a vector subspace of f omega c, and second property, H is endowed with an inner product with respect to which H is a Hilbert space. And the third property is for every lambda belongs to omega, the point evaluation functional on H defined by E lambda f is equal to f lambda, this is bounded. And the Ritz representation theorem ensures that for each lambda in omega, there exists a unique function k lambda in H such that E lambda f that is equal to f lambda that is equal to inner product f k lambda for all f belongs to H. And this identity is called the reproducing property of the reproducing kernel Hilbert space H. The set of all functions k lambda, lambda belongs to omega, is called the set of all reproducing kernels of the reproducing kernel Hilbert space H. And if we normalize the reproducing kernel and denote by k lambda cap, then the collection k lambda cap, this is called the normalized reproducing kernels of the reproducing kernel Hilbert space H. Now I will give the two examples of reproducing kernel Hilbert space. First example is the Cn, the space of all complex n tuples is a reproducing kernel Hilbert space on the set omega, where omega is the collection of natural number from 1 to n, which is a usual inner product on Cn defined by inner product uv, that is equal to summation I is equal to 1 to n ui vi bar, for u is equal to u1 u2 to un, and v is equal to v1 v2 to vn. And let Ej denote the canonical orthonormal basis for Cn, that is Eji that is equal to 1 if I equal to j, and this is equal to 0 if I not equal to j. Then for every u belongs to Cn, we see that uj that is equal to u suffix j, and this is nothing but the inner product u with Ej. And thus the canonical basis of Cn is precisely the set of kernel functions for the point evaluations when we regard Cn as a space of functions. And the second example is the Hardy-Hilbert space on the unit disk, which is defined as the collection of all holomorphic function such that f can be represented as summation n equal to 0 to infinite a n z to the power n with summation n equal to 0 to infinite mod n square. This is finite. And with the inner product fg is given by summation n equal to 0 a n b n bar. Here HOLD is the collection of all holomorphic function on D. And with this operation, Hardy-Hilbert space is also a reproducing kernel Hilbert space. And the kernel function at lambda is given by this, that is k lambda z that is equal to 1 by 1 minus lambda bar z for all lambda belongs to D. The Berezin transform or the Berezin symbol of for any bounded linear operator is a function a tilde from omega to c, which is defined by a tilde lambda that is equal to inner product a k lambda cap for all lambda belongs to omega. And this Berezin symbol is very useful in operator theory and its complex analysis. And the Berezin range is defined as the range of the Berezin transform, that is Berezin range of an operator A that is equal to a tilde lambda where lambda belongs to omega. And the numerical range of any operator A is the collection of all complex number of the form inner product AFF where f belongs to the unit sphere of the Hilbert space. Clearly, the Berezin range is contained in the numerical range of that operator, because the Berezin range is the range of the Berezin transform, and k lambda cap belongs to the unit sphere of the Hilbert space, and so the Berezin range is contained in the numerical range of that operator. Although the Berezin range is contained in the numerical range, but their geometric properties may be different. Now I will give an example, and I recall that the numerical range of an operator is always a convex subset of the complex plane. But in this example, I will show that the Berezin range may not be convex in general. If we consider the matrix A ij, where ij equal to 1 to n, and we considered A as an operator from Cn to Cn, and the Berezin range of A is nothing but the collection of all diagonal elements of the matrix. That is inner product A ei, where I equal to 1 to n. This is the collection of all diagonal elements. Therefore, for any matrix, the Berezin range is convex if and only if all the diagonal elements are equal. That is, A has a constant diagonal. Therefore, the Berezin range is convex only for very special cases. And there is a natural question: let A be any boundary linear operator on a reproducing kernel Hilbert space H, then characterize all boundary linear operators on a reproducing kernel Hilbert space for which the Berezin range is convex. And the question was raised by C.C. Cowen and Felder in 2022, and they characterize when the Berezin range is convex and they characterize some composition of operator for which the Berezin range is convex. And now I will introduce the weighted Bergman space, and I studied the convexity of the Berezin range for some particular classes of composition operator on this weighted Bergman space. For any gamma strictly greater than -1, we considered the positive Borel measure on D by this, and the weighted Bergman space with standard weight is defined as all those holomorphic functions such that this integration with respect to the new measure dA nu, this is finite. And it is also easy to observe that these weighted Bergman space are also a reproducing kernel Hilbert space, with the kernel function is given by this at the point xi belongs to D. And the normalist kernel function is this, that is dividing the kernel function by its norm. Let psi d to d be an analytic self-map, then the composition operator is defined by this C psi f, that is equal to f composition phi, and the composition operators are bounded on the weighted Bergman spaces, and the bound is given by this. Now consider the function psi beta eta w, that is equal to this, where beta belongs to the open unit disks and eta belongs to the boundary of the disks, and these functions are all analytic self-map from D to D. And if we calculate the Berezin transform at the point W, then we get this. That is equation number 2. And now we characterize the convexity for the composition operator with the particular elliptic symbol, that is psi 0 eta w, that is equal to eta w, and we prove that the Berezin range of this class of operator is convex if and only if eta is equal to +1 or -1. First we calculate the Berezin transform at the point W, and we get this. And to prove this result, we need this lemma. First, the number 1 is the Berezin range of C psi 0 eta is singleton if and only if eta is equal to 1, and imaginary part of Berezin range of C psi 0 eta, that is equal to 0 if and only if imaginary part of eta is equal to 0. And this is the proof of this lemma. And now I give a brief sketch of the main result. If we consider W equal to RE to the power I theta, for R belongs to the closed 0 open 1 interval and theta belongs to closed 0 open 2 phi, then the Berezin transform at the point RE to the power I theta is given by this. And if it is equal to 1, then Berezin range of C psi 0 eta, that is equal to, contains the single point 1, and this is convex. If it is equal to -1, then we can calculate and get the Berezin range is open 0 close 1 interval, and this is also a convex set. Now we prove the converse of this result. Suppose that the Berezin range of C psi 0 eta be convex, then we calculate the Berezin transform at the point r e to the power I theta, and this is independent from theta, and we can say that the Berezin range is just a path in C. By the convexity, this implies that the path should be either a single point or a line segment. Now, by the previous lemma, we get that the if Berezin range is a single point, then eta is equal to 1, and next we consider the Berezin range is a line segment. Now from the Berezin transform, we get that the Berezin transform at the point 0, that is equal to 1, and if we take r tending to 1, then we get the Berezin transform equal to 0. Therefore, the line segment passes through the point 1 and is approaches to the origin as r tending to 1. Therefore, the imaginary part of the Berezin range is equal to 0, and by the previous lemma, we can conclude that the imaginary part of eta, that is equal to 0, since eta belongs to the boundary of the unit disk, so we get eta will be either 1 or equal to -1. Thus, the proof is complete. Now study to characterize of the convexity of the Berezin range with this symbol, where beta belongs to the open unit disk. And first we calculate the Berezin transform of the composition operator at the point W. And the first lemma, we just calculate the imaginary part of this Berezin transform and the real part of the Berezin transform on the weighted Bergman spaces. And then in the next lemma, we prove that the Berezin range is closed under complex conjugation. And now I prove the main result, but we cannot prove the result, that is Berezin range is convex even only beta equal to 0. Without this condition, we assume the condition that imaginary part of psi C psi beta 1 tilde W equal to 0 implies that imaginary part of beta bar W equal to 0. If beta equal to 0, then it is clear that Berezin range contains a single point which is convex. Now we prove the converse. Since the Berezin range is closed under complex conjugation and it is convex, therefore we get the real part of the Berezin transform at the point W, it belongs to the Berezin range of the composition operator. And then from the definition of the Berezin range, we get there exists a Z belongs to D which satisfies this relation. And by our condition, this implies that the imaginary part of beta bar Z equal to 0. And therefore, we get Z is equal to r beta for some r in that interval minus 1 by mod beta to 1 by mod beta. And using previous two lemmas and putting the values of Z, we get that the Berezin transform of the composition operator at the point Z is equal to 1 minus r mod beta square to the power gamma plus 2. And therefore, for this collection of Z, that is for r beta, we get the Berezin range is contained in this interval 1 minus mod beta to the power gamma plus 2 to 1 plus mod beta to the power gamma plus 2, and this is away from, this does not contain the origin. And now we calculate the limit of this, the Berezin transform, and if beta not equal to 0, the limit equal to 0, and if beta equal to 0, the limit equal to 1. Thus, when beta not equal to 0, given epsilon which is strictly less than 1 minus mod beta to the power gamma plus 2, there exists a point W which satisfied that the modulus is strictly less than epsilon. And for this W, we get a Z such that the Berezin transform at the Z which is strictly less than epsilon. And this contradicts the fact that the Berezin range is contained in this open interval. Therefore, beta equal to 0. And so we prove that for this case, the Berezin range is convex if and only if beta equal to 0. And we also prove that if we consider gamma in that interval open 0, open -1 to close 0 interval, then the imaginary part of this Berezin transform at the point W if and only if imaginary part of beta bar W equal to 0. That is, these two are equivalent. So for this interval of gamma, we don't need the additional condition. Therefore, if gamma is in the interval -1 to close 0, therefore the operator for the composition operator in the weighted Bergman space, we get that the Berezin range is convex if and only if beta equal to 0. Now we establish that 0 lies in the closure of the Berezin range of the composition operator C psi, yet it is not contained in the Berezin range itself. Let psi be a non-identity holomorphic self-map on D, then 0 contained in the closure of the Berezin range of C phi, but it is not contained in the Berezin range of C phi. Now for any W belongs to D, we just calculate the Berezin transform at the point W, and we get this. Since psi is not an identity map on D, then there exists a point W naught in the boundary of the unit disc. We say the boundary is T, such that the radial limit of psi exists at the point W with psi of W naught. This is not equal to W naught. And thus, from this equation 5, we get, taking W radially approaches to W naught, we get that the Berezin transform is tending to 0. Therefore, 0 belongs to the Berezin range of C psi closure. Again, we take the modulus of the Berezin transform and we get that this is strictly greater than 0, and therefore we get that the 0 does not belongs to the Berezin range of C psi. Thus, the result is proved. Now I will discuss some open problems, and the previous results motivates us this problem, that is, characterize all those phi and psi such that the 0 belongs to the Berezin range of C psi phi closure, but 0 does not belongs to the Berezin range of C psi phi. Then characterize all those psi and phi such that 0 contained in the Berezin range of C psi phi. And the third problem is characterize all those psi phi such that 0 is contained in the interior of the Berezin range of C psi and phi. And the second problem is, for any gamma strictly greater than -1, is it true that the Berezin range of this composition operator is convex if and only if beta equal to 0? This is the second problem. And the third problem is characterize all those beta and eta such that the Berezin range is a convex subset of C. And the fourth problem is determine conditions under which the Berezin range of a composition operator induced by finite Blaschke product factors is convex. These are the references, and this is the main paper of Cowen and Felder, where they first discuss about this problem, the convexity of the Berezin range. And this is our recently published paper, where we studied the convexity of the Berezin range of Toeplage and weighted composition operator on the weighted Bergman spaces. Thank you.